All right, welcome back. Today is November the 13th, and it's Friday the 13th. Those of you who are superstitious, it's okay. I'm just a little stitious, not much superstitious at all. Matter of fact, my twins were born on April the 13th, so I don't feel that 13 is a bad day exactly, but it's actually a pretty good day for a quiz. So hopefully everybody does well, or the majority at least. Quiz on the 13th. Well planned. All right. So let me see the comparison here with the morning class with you guys. Where do I need to stop? Okay. On the letter F for the number 3 problem. All right. So let's go. Let's hit the ground running here. Yeah, we have a lot of problems. All right. So let's get started here. So last time when we met, we talked about the use of thionyl chloride, and that is an SN2. That's a pure SN2 reaction with inversion of configuration. And it's an SN2 because, where is it? Because the chlorine right here does the SN2 attack. All right? All right, so let's go back over here. And so we have now gonna draw the entire skeleton of carbons here. That doesn't change, but this group here will change. All right. All right, so that's one. And then the next one is H. So what is the next example of? Have an alcohol and phosphoric acid. Dehydration of alcohols. Is that an E1 or E2? E1. So this is an E1 reaction. Dehydration of alcohols. And so there's only one H that I can take or grab, is this one. So this reaction goes via a carbocation intermediate, forms a really stable, let me do black, really stable benzylic carbocation. When this group, this OH turns into a water leaving group, it leaving a benzylic. This is a benzylic carbocation intermediate, really stable. And then this H is taken by the conjugate base of phosphoric acid. And that's gonna make anybody knows the name for that molecule by any chance? It's a polymer used to make styrofoam. Styrene, very good, excellent. This is styrene. That's the name of that alkene. Excellent. All right, so the next problem is POCl3. I already went through the mechanism for that. Let's revise it, because on the mechanism for that, I think I had regular bonds here last time, but make sure, I don't regular bonds, but make sure that you notice that this is an anti-periplanar grab also. So it grabs the H that is opposite to this bond right here. This bond is up, So it'll take the H, and then these electrons from this bond, these two, will make that double bond there on the P and the O. It's a really good driving force. The formation of that P double bond O, it's one of the strongest bonds in nature. Not the strongest, but on the strongest list is way up there on the top, maybe third or something. Yeah. So always remember that it's an anti-periplanar grab. All right. So let me go back to here. All right. So if that is the case, we look for the anti-periplanar hydrogens. Check this one out. This one is up. So that would be useless. It will be a zinc grab. It needs to be anti. So it'll be one of these. So it'll be this one that is down, and there's another one here that is up. So you grab the one in the middle, this one. That's the one that we're gonna grab. So when we grab this one, then we can do that mechanism that's kind of long. But anyway, we make only one product here. Notice that we cannot grab, this guy cannot be grabbed, or in a way that one. Yeah. So you only make one product, and that product has chirality all over the place. One there and one there. All right. PBr3. Notice that this reaction is actually an E. This is an E2. All right. PBr3. What does it do? Converts an OH into Br, right? So, does it do it with inversion of configuration? Yes, it's an SN2. All right, so we had this, and so we had that, and now the bromine, it's gonna come from the opposite side. The bromine that is kicked off here is gonna come from the opposite side to kick off the oxygen that's gonna be transferred to the phosphorus, and it's gonna make a P double bond O, remember? So then we get this molecule. 100% inversion of configuration. Went from an axial to an equatorial. All right. All right. And if you are listening online, make sure you ask questions too. I have volume here up to 100% so I can listen to you. All right. What is the name of this reaction K? Anybody? So ring opening of epoxides. When you see an epoxide, we're going to nuke it. All right. And so there's two ways of doing it. One way is with basic conditions, and another one's with acidic conditions. What conditions do we have here? Basic or acidic? Basic. The first step is independent, so basic condition, right? So you have that this potassium is a spectator ion. All right, so for basic conditions, I'm going to write that down. So these are basic conditions. The protonation happens at a second step. That's why it says 2, and then diluted hydronium ion. On the basic condition, this is a pure SN2 reaction. Pure SN2. All right, I have a question. Where would the nucleophile attack? Option number 1 or option number 2 here? Option number 2. Why is that? Least substituted. Very good. So least substituted comes, attacks right there. opens this up and check this out. So what we have is we have made a new nucleophilic attack here, and then this methyl is towards us, and then the methyl is towards the back, and the oxygen with a negative charge goes there. So that's the first step. Second step, we add the acid, and that just puts an H right there, and that's the final product. All right. Pure SN2, there is that carbon was flipped. The configuration was flipped, but it's not a chiral carbon, so it doesn't show it. But there was 100% inversion of configuration there. So let's do the next examples. Problem number 2, complete the equations for the following reactions. All right, you're going to see that zinc chloride is also a useful reagent to convert primary alcohols into primary alkyl halides. All right, so what it does is, since this is an ionic compound, the zinc will coordinate with the, so you have something like this, where actually these ones are, this is zinc 2 plus, and then you have the minus here and the minus here. So that pull, the zinc acts as a Lewis acid, and it pulls the electrons from the oxygen towards it, making this bond breakable. How cool is that? It pulls it, and then one of the chlorines goes and attacks and gives those 2 electrons to the oxygen. All right. And then you get 1, 2, 3, 4, 5, 6. It's 5 carbons in a chlorine. All right. Okay. So this is also an SN2 reaction. Lots of SN2s. This chapter kind of like blends together with the previous one because there's a continuity there. All right, let's do the next problem. Notice that for the next problem, we have something called tosyl chloride. Tosyl chloride looks like this. All right, so this reaction is not an SN2 reaction. It's simply a protection of an alcohol. All right, so we use that to convert the OH, which is a bad leaving group, into a good leaving group with the tosylate group. All right, check this out. This is the mode of the reaction. The lone pair from the oxygen goes and attacks the sulfur. The sulfur is a hypervalent atom, which has 2, 4, 8, 12 electrons around it, right? So it has a lot of electrons. And what is the hybridization for that sulfur group? sp3d, because it has 4 directions. You do sp3, wait, sp. Oh, you're right. There's only 4. Yeah, you're right. You're right. sp3d. Sorry, sp3. My man. Good job. Oh, my dyslexia is killing me. Yeah. So there's 4 directions. So it's sp3. Very good. But it's a flat molecule. It's not like a tetrahedral or anything like that. All right. So that what this does is swings up, swings down, and kicks off the chlorine. And so what we get is we get 1, 2, H, and then the oxygen is attached now to that, like this. Sulfur likes oxygen, so the alcohol provides that. And so you make that, or you can say, which is the same thing as just simply say OTS. This is the TS part, the tussle part. All right. So that'll be the final product for that. All right. What do we have on the next example? What type of reaction is that? You have a secondary alcohol and you have acid to it. But this is not a dehydrating agent. This is not a sulfuric or phosphoric acid. It's hydrobromic acid, which is acidic, but it's not going to dehydrate. What is it going to do then? If it doesn't dehydrate, what's the opposite to DE1? SN1, exactly right. So this would be a pure SN1 reaction where the oxygen grabs this H, kicks off the bromine, the water molecule leaves, and now you have a secondary carbocation. Thank you. I was like, thank you. Got stuck in space. I was thinking carbonyl. I get those two terms confused, carbonyl and carbocation. But yeah, thanks. Can this molecule make a better secondary? Better than secondary? Yes, it can. So here we'll have a 1,2 methyl shift. It's the same as alkyl shift, so let's say CH3 shift, and now we're here, right here. All right, and where would the plus go? It will go right there. All right, and so remember the bromine was kicked off. It's really back with a vengeance. Say, yeah, you kicked me out of my house. Now I'm gonna kick you back. And goes and attacks there. Yes, sir.
Do you ever have like a 1,2 isopropyl shift?
1,2 isopropyl.
Like, is it just methyl?
Oh, that's a good idea.
Yeah, and then how will it choose if there's like an isopropyl or a...
I'm sure you can do. There's a reaction called the pinnacle rearrangement. And you can, it's just for like ring expanding. I'm pretty sure that an isopropyl alkyl shift can happen. Yeah, it's a little bit bulky, but it can happen. Yeah, usually I've seen it like methyl and ethanol. I mean, and methyl and ethyl. But yeah, so let's see here. Our final product will look like this, reorganized. All right. Okay. All right. So what's the next reaction is again POCl3. It's an E2 reaction. Dehydration. Look out for the anti-periplanar hydrogen. So right now, your options are this one. This H is not good. It's on the same plane as the leaving group. So use the one right here that is up. You have one up there and one down. Only this one will be grabbed. All right. So you're gonna do that get rid of the OH and form a double bond right here. And so it's the only product that is formed from this reaction. This stereocenter is retained, and all you have to do is put a double bond there. All right. Next, what type of reactions then? What is the name of that reaction? Ring opening of epoxides. Is it under basic or acidic conditions? Acidic, right? Yes. Acidic conditions. I'm writing it on in red. pH for acidic is red. pH for basic is blue. So I use that. Acidic conditions. All right. What type of reaction is this? Between SN1, SN2, E1, E2, or SN2 borderline? Borderline, right? So it's an SN2 borderline. Somehow every time I teach this, Madonna's song comes to mind, Borderline. I can hear the intro in my head. You know, like this, the synthesizer. So borderline. And yeah. So if that's the case, question here. We'll go to option number, the nucleophilic attack. So what's going to nucleophile? So this oxygen grabs the H and the bromine is kicked off. All right? So option number 1 or option number 2, where does the attack go for the SN2 borderline? The most substituted, exactly right, and that would be 1. So your bromine will attack right there, and it will open up this ring. It'll come from the opposite direction where the ring is. So if the ring is up, the attack will come from the bottom, and vice versa. So notice that now that methyl group is going to be pushed up, but it still be facing us. All right? So it'll look something like this. So here's the anti-periplanar option. So this is what we're making. This is my anti-periplanar. Oh, look how beautiful that looks. Like 120 degrees perfect. No, I'm just kidding. So here, this methyl group will be up, and this H will be towards the back. And that is the final product of that. Notice that for the SN2 borderline is both. It behaves as an SN2, SN1. It gives you the SN1 product because the bromine goes where the most substituted carbon goes, but it gives you a inversion of configuration. It flips the configuration. Therefore, it acts as an SN2 also. That's why they call it the SN2 borderline. All right. Very good. What do we have here? So this is in the next reaction. We are treating a tertiary alcohol with hydrogen chloride. What is that going to be? What type of reaction is that? SN1. Very good. We don't have a dehydrating agent, but we have a good acid. And the reason why hydrochloric acid is not a good dehydrating agent is because chlorine is a good nucleophile. As the inverse that happens with sulfuric and phosphoric acid, those guys, their conjugate bases are simply bases. All right, what am I getting here? Oh, this one. All right, I have 7-member rings, so I usually go 1, 2, 3. I put like the roof of a house, and then I make a little boat here. So here's the roof of the house, and here's my boat, and then I just connect them. All right, and so here I will have that. Oh, check this out. Yeah, this will be racemic. So yeah, we'll make this. That's it. and it's racemic. Is there a plane of symmetry? Yes, there's a plane of symmetry. So this molecule doesn't have chirality at all. All right, but the next one does. All right. So yeah, this is achiral, so it's non-racemic. It's just achiral. All right, let's do the next one. We have a chiral center here. I put a little star on it. If you have 4 different things attached, put a star on it. So you have 4 different groups attached. Notice that the distance from here to the ring is different than from here to here. So that makes these 2 groups different. And so OH, what it likes to do is a base, sees an acid, grabs the H, kicks off the chlorine, and now you have this intermediate. Yeah, this methyl with a plus right there. So this is a tertiary carbocation. The molecule is happy. And then how many products can we make from this? 2 products. Excellent. Your chlorine, color coding everything, can do a top or a bottom attack. And you get 2 products. To speed up, I just draw the skeletons first. And then I put the furnishers. So 1 up, 1 down, 1 down, and 1 up. So those are the 2 products you get.
So like save time, could you just draw a squiggly methyl?
Yeah, exactly right. Same thing as Ben says, you save time by saying, you can do 2 things. You can do this. Methyl here, no. You do methyl and squiggly, or both squiggly. You know they both change, or you can do and say you can do this. If you do this also, it's perfect. And say the word racemic. Those are the ways you can draw this. Those are your 3 options. All right. And that was, what type of reaction was that? SN1. Why? Tertiary alkyl halide, polar protic solvent. Yeah, so we're good. All right. So the next example is a protection of an alcohol again. We're switching it from an alcohol to a tosyl group. So this chiral centers stay chiral. And the OH too. There's no inversion here because we're just protecting it. Just gonna write it like that. You get the idea.
So like, what's the purpose of preserving it for a long time?
No, you want to turn it into a good living group. Yeah, OH is a horrible living group. It's poor. Yeah, so by turning it into a tosyl group or a methyl group, it's really good. It's almost this guy. Think of this. I haven't said that, but think of this as the equivalent of a big halogen, or like a big Cl or bromine group. All right. Yes, sir.
So what reaction is
It's not SN1 or SN2. Mm, what is this? This will be,
Like what you said, like when you insert something, it's like an insertion.
yeah, it's an insertion or like an addition, elimination. This could be falling into that. So you add it. It's like when we add it here. Notice that we added to it, to the sulfur, right here, this bond, but then we eliminated the chlorine. So it's like addition, elimination kind of deal. It doesn't have a name for it. All right, how about the next example? Oh, yeah, so it's not SN2. What about the next example? Secondary alcohol with HBr. What are you making there? SN1. Polar product solvent and also happens to be an acid. The oxygen grabs the H, kicks out the bromine, and then water leaves, and then you made this secondary carbocation, which is the best you can do here. You can only do secondaries and primaries. And then the bromine is angry, back with a vengeance, and kicks in. It's like your older brother if he leaves the house to go to like the army or college and comes back and you have his room. You're gonna get out of there very fast. Yeah, that has happened, especially to bigger families. All right, so we get that. All right, so the next one we have is another example of POCl3. Notice that I just keep on repeating examples so that you build that muscle memory. The only thing you had to worry about here, I didn't put the oxygen here as up or down or wedge or dash. So you know that the H that you're going to withdraw from here will be the opposite side. So you have two, so you don't have to worry about it. So you'll be kicking this out and forming a double bond right there. And that's the only place that it can go. So you make that. All right. All right. So the next example is the following. So ring opening of an epoxide again. What kind of conditions we have here? Acidic or basic? Huh? Acidic. Yeah, we have sulfuric acid there. So one drop of it is enough to make it acidic because that thing is so strong. Acidic conditions. And what kind of type of reaction is that then? SN2 borderline. So, step one, the epoxide gets protonated. Then, step two, the nucleophile, which is neutral, attacks where? The most substituted one, yes, right there. And so it's going to open up this epoxide, and then we'll make this. So get used to this, doing this. So do your anti-periplanar. That way you don't mess up. Then the next thing you do here, you put your OCH3. Notice that you had to lose one hydrogen there. So another molecule of methanol has to come in and grab that H. And then push up the same stereochemistry that you have, but just push it up. So one up and one down like that, and you're done. All right. Let me fix this. Let me make it look nicer. So I'm gonna put this one so you can visualize it better. So let's put this closer to us here. I'm gonna get used to that. And then the one that is away from us there. That looks beautiful. All right. All right. What is the next example? I found that the publisher had a problem with this problem. The answer was wrong. So what are we dealing with here? Type of reaction. SN1. All right. So we do the SN1. We grab the H, kick off the bromine. Then we make water as a leaving group. That water leaves, right? You're visualizing that? Then you have the following thing. You have a plus right here. And this is a secondary carbocation. Can we make a better carbocation? Yes. So let's do it. First, hydride shift. 1,2 hydride shift. This one of these H's will jump. So this one will jump there. And now the carbocation goes here, right? It migrates there. It's still secondary. And then we do another 1,2 hydride shift using this H. This H jumps and forms the best of all of those carbocations. A tertiary C+. And where's the bromine? Where's that angry bromine? I mean, if you get a backside kick, I mean, you gotta be pretty angry, right? And so you go, and he attacks back. And so this is the final product. Or not the final product. I should not say that. I would say the major product. Major. What are other products that we can form that are minor? So, wherever this carbon, wherever the carbocation is, put a bromine there. Yeah. All right. We have 10 more minutes. So I need to get to the letter F here. I think it's possible. All right, help me out. Okay, so now we're getting more proficient on this. We can press the pedal to the metal. All right, and let's see what we got. So PBr3, what does that do? Converts an OH into a bromine. Question I have, will it change the configuration? Yeah, it changes it. Yeah. It's an SN2. This is an SN2 reaction. Next one. Acidic or basic conditions. Ring opening of an epoxide. Acidic. Acidic conditions means in type SN2 borderlines. So this is SN2 borderline. And oh, yes. And then so what is the nucleophile? The water. Water is gonna come, it's neutral, so it's not as strong. It's gonna kick there and open up the epoxide there. So basically, the first step, I'm gonna do this one stepwise because I didn't do it last time. The oxygen grabs an H from the epoxide, the oxygen from the epoxide grabs an H, turns those electrons there, and now you made this elongation called alkoxonium ion. Remember that? So this wants to break because this carbon now is partially plus. Methyl group and an H going that way. And now the water nucleophile goes and attacks here. No, not there. Attacks right there. And then opens up the bond that is breaking. And so you end up with, do your anti-periplanar, OH up here. The new OH will come out here after you deprotonate from the water. And then one methyl will be up. I'm gonna put it right there so that it looks nice. And the H will go towards the back. And that's your final product. All right. Okay, notice that A and C are the same thing. So let's convert it into different things. And so, yeah, so we're gonna get, without further ado, let's just write the answer because we have something very, very similar on top. All right, next example is tosylation of an alcohol. We have pyridine. Pyridine acts as pyridine is in charge of grabbing this H to make the reaction, make the molecule neutral. So it's going to do this. Keeps the configuration up, oxygen, and the tosyl group will be there. How cool is that? Super duper cool. All right, this is on the notes. So if I have an alcohol and add sodium hydride, what kind of reaction is that to start?
Turn the alcohol to water.
No, check this out. So sodium, whenever you see sodium, what is the first thing you need to do? Cross it out, get rid of it. Then you'll notice that you're dealing with a hydride. That sodium hydride, it's a base, and so it's going to find an alcohol, an acid. It's an acid-base reaction. The acid is the H on the OH, right? It's gonna go for it, grabs it, takes it, and then 1, 2, 3, 4, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, and an oxygen. This oxygen now becomes negative. The sodium that was being a spectator ion is right there next to it. And check this one out. This reaction is so irreversible because we form hydrogen gas and it will escape. This type of reaction you have to run under nitrogen because if there is heat or spark, we can blow up the lab. Hydrogen gas is extremely flammable and explosive. But nonetheless, if you take precautions, you can run them. You can run them. Yeah. Yeah. So, So we have 4 more minutes, and we got to letter F. What type of reaction is this? Ring opening of an epoxide under basic conditions. Yes. So I have parentheses. Basic conditions. So that is a pure SN2 event. acid potassium. That is a spectator ion. Goodbye. Then put a minus charge on the oxygen. And then the oxygen is going to go option number 1 here or option number 2. Option number 2, the least substituted carbon. Why is it the least substituted carbon? Check this out. Let's dissect these carbons. This carbon in red has 1, 2, 3, and 4 substitutions. Now, this carbon in red, in green, has 1, 2, 3 substitutions because you have a hydrogen that is down that doesn't count. So 4 versus 3, the one that has 3 is less. That's where the substitution will go. So I'm gonna delete this, all that, and attack, and it's gonna open up. Notice that what's happening here to the stereochemistry. That's where you have to be careful. Draw your 6-member cyclohexane. Notice that this methyl stays down. The alkoxide opens up like that. And the new group, is it down or up? The new OH group, right here, on this carbon. Down, exactly right. It comes from the opposite side where that epoxide ring was. So you're here. This is step 1, and then step 2 is adding a little bit diluted acid in water. That simply puts an H right there, and you're done with that reaction. So that's the second step, protonation. It's also known as workup. Okay. Wow, I have one more minute to spare. All right. So I have hydroiodic acid and secondary alcohol. What kind of reaction am I going to make here? SN1. So this is an SN1 event. And how many products am I going to get? Since I have chirality here, and this is also chiral. So
Can't you do a carbon rearrangement?
you can. The literature didn't give me that, but yes, you can. Let's draw it. We don't need to go with what the literature says. Sometimes these guys are wrong. We can revise them. Very good. So this one will do. These are the 4 products that will do. So holy mackerel, it could do 4 products. It's gonna do 2 hydride shifts until you get to here. 1 like that and 1 down like that. 1. This will be the major products. And this will be iodine. We need to stick with what we preach. The other possibilities are where the OH is already there. So these 2 will be major. 50-50. Because there is carbocation rearrangements. And the second one will be, let me make this smaller. Methyl up and iodine up, or methyl up, that doesn't change, and iodine down. Also in 50-50 mixture.
Couldn't you have one in the middle? Because that's the shit.
That you can also have 2 in the middle. Yes, sir. Yes, sir. Yeah, let's draw them. So you can also have.
So this isn't very efficient if you use 6 products.
Oh no, this is awful. This is good paper chemistry. This will be up, and this will be with the intermediate, one of the intermediate carbocations. This will be still up, and this will be down. So again, this will also be 50-50 with themselves. But it's becoming really hard to say 50-50 so many times, so let's just get rid of that. It's not 50-50 at this point. Might be like, I don't know, 50-25, 12.5 to 8.5 by the time it gets there. Yeah. All right. We're going to stop here, guys. Let me stop the recording. Have a wonderful day.